Okay, so far we have talked about the protons, the neutrons, the electrons as far as placement, as far as mass, and as far as count. Now let's just focus on the electrons for a little bit here. This section is called electron configuration, and what configuration just means is it's the arrangement. Right? It's the arrangement of the electrons within the atom. So the first model of importance here on this topic is what we call the Bohr model. And I mentioned this before. The Bohr model shows the atom with the electrons separated into different levels. And depending on how many electrons there are, the atom is going to need more levels. So if it's a really small atom with a very few electrons, it's not going to need very many levels. Right? You might have seen something like similar to this in 8th grade, where the first orbit, we don't really call it orbit. The main term that we use is going to be energy level. You might see the word shell, okay, but really energy level is the main term we'll be using. So the first energy level can hold 2 electrons. So that's right here. Energy level 1 is the first level that's closest to the nucleus, and it can only hold 2 electrons. The second level, right, is the second circle, and this can hold 8. The third is here, the third ring. It can actually hold more than 8, but now it starts to get complicated. All right, but the bottom line is the higher the number energy level, the more electrons can hold. Does that make sense? Yeah? Okay. All right, so for hydrogen, because hydrogen only has 1 proton and 1 electron, this is what a simple Bohr diagram would look like. 1 proton, 1 electron, doesn't get very complicated. But if we look at oxygen, so oxygen has 8 protons, and it's going to have 8 electrons. So the nucleus, of course, is where the protons are and where the neutrons are. So here's our nucleus. Now, this first ring, this is energy level 1. And remember we said that energy level 1 can only hold 2 electrons, and that's why you see 2 dots there. Energy level 2 can hold 8 electrons, and we only have 6 electrons there, and that's okay. It doesn't have to be full. The point is it can hold up to 8. Okay. This term might pop up here and there. The term quantum number. Quantum number, there's lots of different quantum numbers, but the only quantum number we're really going to use is n. And I already told you that n equals energy level, so don't be thrown off if you see that term, quantum number. Okay, it's primarily talking about the energy level. Okay, now let's look at something like aluminum. So aluminum has 13 protons, 13 electrons. So if we drew a Bohr diagram for aluminum, in the nucleus, 13 protons, if the mass is 27, that means we have 14 neutrons. So here's the nucleus. Okay, so energy level 1, we expect 2 electrons. Energy level 2, we're going to see 8 electrons in energy level 2. Okay, so we have to account for all of the electrons, and right now I've only shown 10. So now we extend into the third energy level. These circles are not perfect. It's okay. So what do we have left? How many go in energy level 3? 3. 1, 2, 3. Where I place the electrons doesn't really matter. This is just like a rough count. All right, so are you guys okay with Bohr diagrams? All right, this is the most basic representation of where electrons are in an atom. Okay, so how many energy levels will have electrons in them? Well, we use energy levels 1, 2, and 3, so it's going to be 3. Okay, but we're not really going to focus on Bohr diagrams. We're just using that as a starting point. The organization of electrons is actually a lot more complicated than just a circular orbit. So the shapes, you know what, I'm going to add a page here, and I'm going to kind of explain this a little differently, because I think we jump into some deep stuff here. All right, I'm going to start with a blank page, real simple, okay? I'm going to write 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7, okay? So these represent the levels. Now, you know and you saw that the higher number the energy level was, the more electrons could be held. Now, the reason why more electrons can be held is because you literally have more geometric space, right? The wider, just like when you order a pizza, right? It's a large is significantly bigger than a medium, right? Okay, so this is geometric growth. It's three-dimensional. So in energy level 1, there's one place where we can place electrons, and this is called a sublevel. And there's different types of sublevels. There's S, there's P, there's D, there's F, and there might be others, but let's just stick with that for now. So each of these sublevels have a certain number of electrons that they can hold. So sublevel S can only hold 2 electrons. In energy level 1, there is one sublevel, and it holds 2 electrons. So far, this makes sense because we've known that energy level 1 can only hold 2 electrons. So let's move on to energy level 2. In energy level 2, because it's bigger than energy level 1, it's going to have 2 sublevels. It's going to have the S, because that's like defaults to everyone. Everyone has S. And then it has this new one called P. So this sublevel P has a capacity of 6 electrons. So in energy level 2, if you see that it has S and P sublevels, you can add up the capacities, and now you realize, okay, well, energy level 2 can hold 8 electrons. Because there's 2, it's kind of like subfolders. One folder holds 2, one folder holds 6, but both of those folders are in the same level. So the whole level holds 8. Okay? In energy level 3, there's S, there's P, and there's this new one called D. Now you're familiar with S and you're familiar with P now, but D is new. The capacity of D is 10 electrons. So what's the total capacity of energy level 3? 18, right. Moving on. In energy level 4, there's 4S, 4P, 4D, and 4F. Look at the pattern. Can anyone guess as to how many F can hold? 14, that's right. Each sublevel increases by 4 electrons. Okay, and then, if I were to fill out the rest of this following the pattern, I'm not going to write every single one out. Whoops. I'm just going to write the ones that I know that we need. Okay. I know I stopped writing for 6. Technically, if we could keep writing, so 6F, 6G, 6H, and so on. But as you'll see, we don't actually need all of those, right? The higher the energy level, we don't actually need all of those extra subshells, and you'll see why in just a moment. Okay, so let's talk about the S subshell. Now that you kind of understand, you know the hierarchy here, and you know that each new level has more sublevels, and each new sublevel is bigger than any previously seen sublevel. Okay? So, S subshells look like spheres. And I did mention they're three-dimensional, so it's on an XYZ plane. Okay? Now, there's this term orbital. The word orbital is like a partition of a sublevel. Each orbital holds 2 electrons max. So, when we look at our S sublevel contains 1 orbital, and that explains why S only holds 2 electrons, because there's only 1 orbital there, and each orbital only holds 2 electrons. So I guess if we want to jump back to that little chart that we made up here, and we write number of orbitals, we can fill that in and say that S only has 1 orbital. Okay? So a P subshell contains 3 orbitals, and their shape is kind of weird. P subshell is dumbbell shaped. So there's 3 orbitals, one that lies on the x-axis, one that lies on the y-axis, and one that lies on the z-axis. Of course, the z-axis is coming out towards you and going into the screen. XYZ plane. Now, these dumbbells, what this means is that in this space, is where the electrons exist. So these, it looks like lobes, okay? So both of those lobes on the left side and the right side, electrons, if they're present, they're going to be there. And the same thing with the y-axis here and here, same thing with the z-axis here and here. Now, the reason why it's these funny shapes and not a perfect sphere has to do with some quantum mathematics and the calculation of the waveform of the electron, because the electron, when it moves, it doesn't just move randomly like a bee or a fly. It actually has to move in a way that meshes with the configuration of its wavelength. And so because of that, it's restricted to where it can exist. We're not going to do any of that, but there is a mathematical reason why that shape looks like the way it does. Okay, you ever seen that toy? It's like, I don't know if it's a Rubik's brand toy, but it's basically like a loop, but it's segmented plastic, and you can bend it all sorts of different ways and make it look like a T, and make it look like an O, and make it look like, you know what I'm talking about? Okay, so based on its structure and based on those angles, there's only certain shapes that it can take. Well, think of the electron where it can exist as the same thing. It can only exist in certain angles in certain places. That's why the shape looks like the way it does. Okay, so there are 3 orbitals, and each one can hold 2 electrons. So when you add them up, the P sublevel holds 6. So we go back and update our chart. The P sublevel holds 3 orbitals. And since we're here, can you deduce how many orbitals there are in D? There would be 5. In F, there would be 7. If there were a G, I'm saying theoretically, because actually G has not been observed directly, but if there were a G, what would the capacity be and how many orbitals would there be? Yes. So there's a pattern here. Okay. So Level 1 only has one type of subshell. It's S. Level 2 has two types of subshells, both S and P. And since they're in energy level 2, they're named 2S and 2P. Energy level 3 has three sublevels. Okay, and we already talked about the capacities. So, how many orbitals are there in each of these? We already kind of addressed these. These are in the table above, right? 1, 3, 5, 7. So these are what the d orbitals look like. See the 5 different orientations? Now these are more complicated than the previous ones, right? So now you're talking about three-dimensional spaces at angles between the axes. And you don't have to remember these weird names, okay? That's not really the point. The main thing is you understand that in a d sublevel there are 5 orbitals and each one can hold 2 electrons. F's, predictably, get even crazier, and so each orbital in F is even more fractured and more splintered than we saw before. Again, it's not the point. The main point is that there's 7 orbitals and each one holds 2 electrons. Okay, so here's them all, kind of a hierarchy from simplest to most complicated. Okay. The animation is not going to show up in my notability here, but it's okay. We'll place the link in the video. So what is the point of all this? Why do we even talk about this? This is kind of weird. So here's what we actually use this for. Okay. We are using electron configurations as bookkeeping. So now I'm going to find another space to... Actually, here, we'll jump here. We are going to use this knowledge of the electrons and the levels because we need to place the electrons for every element in order. We need to account for them. We need to know their hierarchy. We need to know where they're going to be found. Because if we know where the electrons in an element are going to be found, then we can make predictions about how it's going to react. And that's the key. Figuring out and predicting how these are going to react. So, this is how we do this. If I pick an element, a simple element like helium, I look up helium, I see its atomic number's 2, that tells me it has 2 electrons. So, you always start writing your electrons with 1s, because 1s is the lowest possible energy level. This concept is called the Aufbau principle. All right, that's a term you need to know. Always start counting your electrons from the lowest energy level, and your lowest energy level is 1s. Okay. That wasn't bad. So we write 1s and we write a 2 because 2 indicates there's 2 electrons in 1s. Sulfur. Sulfur has 16 electrons. So if we look at this diagram, the arrow diagram again, this is the same one that we wrote earlier. Notice that we have cascading arrows coming down at an angle. And the order, these angles for these arrows are here for a reason. This is how we read this. We start by reading the first arrow from the top right to the bottom left. And we end up at 1s. And every time an arrow terminates, we start the new arrow. So the first sublevel of everything, the lowest, is 1s. After 1s, if we have more electrons to count, then we start the second arrow, and that takes us to 2s. So 2s is the second lowest. And then that arrow is done, so then we start a third arrow, and that third arrow takes us to 2p. And if 2p is full and we still have to count more electrons, then we progress on to 3s, and that arrow ends. And then if we have more electrons, we start the next arrow. We come down to 3p, and then 4s, new arrow, 3d, 4p, 5s. After 5s comes 4d, 6p, 6s, 4f, 5d, 6p, 7s. And notice that this isn't complete. We didn't finish this, but if we did, it would look like this. But you notice I did not write 8. I didn't write 8s. And that's because there is no known element with enough electrons to start the 8th energy level. That is why your periodic table only has 7 rows. 1, 2, 3, 4, 5, 6, 7. If we had an 8th, it would start here. Okay? So, looking at the periodic table. This first chunk, energy here, let's number these. 1, 2, 3, 4, 5, 6, 7. There are 4 distinct areas on the periodic table that have a category. The S columns are the first 2 columns. The P columns are the 6 to the right side, the tall 6 to the right. The middle are the D's, and guess what the bottom row of 14 are? F's. Now, the periodic table that I hand out to you looks like this. And this is done out of convenience so that it fits better on an 8 by 11 sheet of paper. But the real periodic table looks like the one that's out painted on the hallway that looks like this. So, just kind of follow along with me here. I'm going to start here, and I'm going to read this like a typewriter from left to right. Do you guys know what a typewriter is? Okay. Have you ever seen one, heard one?
Yeah.
Okay. So, you know when it gets to the end, you have to slide the roll back. Okay? So, I'm going to read from left to right, and every time I get to the right, I'm going to start a new row. So watch. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p. Where have you heard this before? This is the same thing as this. When you read the periodic table left to right, it is the same thing as reading this diagram with the arrows. This is what we call order of fill, and it's very important you follow it. It's pretty much the only way to get these right, is that you have to follow this. So, what does that even mean? How do you even follow this? Okay, so now you know enough, I think, to make sense of this. So I'm going to pick an element. I'm going to use fluorine. Fluorine has how many electrons? 9. Okay. Using the order of fill and using the knowledge of how many electrons are filled in each sublevel, I'm going to sort and organize the electrons in fluorine. You always start at the same place. 1s, and since S can hold 2, I put a 2 up at the top. And S is full now that it has 2, so now I move on to the next one. What is the next sublevel? 2s. And since it's S again, and S holds 2, we put a 2 there. What's after 2s? 2p. And p's, so let's stop and count our electrons so far. I have to account for 9 electrons, and so far I have accounted for 4, which means I have 5 more to place. What is the capacity of P? 6. But how many more do I have to place? 5. So I just put a 5. You don't have to fill. The last one you're in is just where you end, right? And the last one you're in might not be full, and that's okay. This is what we call SPDF notation. It's a cataloging of where the electrons are in an atom. And it can be done for every single element as long as you follow this order and this pattern. So, let's do a couple. Let's do chromium. Chromium is element 24. 24 electrons. Okay, so we always start the same way. 1s2. After 1s2 comes what? 2s2. After that, 2p6. Okay, I have accounted for 10 so far. I have 14 more to go. Next after 2p? 3s2. Okay, that is 12 so far. After 3s? 3p6. Okay, so that's 18. What's next? 4s2. Okay, that's 20. 3d4. And we're done. Now, anybody notice anything weird? Yeah, like it almost seems like it went out of order there for a little bit. It went from 3p to 4, but then went back to 3d. Okay, so this is one of the reasons why we need an order of fill, because there's some weird changes, some weird hiccups in the pattern. If these hiccups didn't happen, this would be very easy. You wouldn't need a diagram. You would just know to go in numerical order. But because there's these weird inconsistencies, that's why we need the pattern. The reason why is because of this. This diagram here, the bottom, the very bottom is the nucleus, okay? So nucleus at the bottom. In energy level 1, you only see one circle there. That should make sense because that's 1s. And as I go from bottom to top, I'm increasing the distance from the nucleus, and that also means that we're increasing the energy levels, right? Higher energy levels. So, the Aufbau principle says you have to start your organization of your electrons from the lowest to the highest. So the lowest is 1s, and then there's 2s, and then there's 2p, and then there's 3s. No surprises so far. And then there's 3p. But look, right here, 4s is actually a little bit closer to the nucleus, a little bit lower in average energy than 3d. And that is why we organize the electrons by putting them in 4s first before 3d. And then after 3d comes 4p. And then 5s, and then 4d, and it gets kind of crazier from here. These levels start to overlap, and when they overlap, it gets confusing. So, that's why, if we follow the diagram, we'll be in good shape. Okay, so, let me give you a couple, and here, let's add a page. Let me give you a couple, and then see how you do, and then we'll check. Okay? So we'll do 2. Gallium, which is element 31, and iodine, which is element 53. So take a minute or two, follow the chart, work your way through those.